Good morning, ladies and gentlemen. Assalamu alaikum. You're very welcome to today's session. My name is Daniel McCrae. I'll be your chair, bringing you through the talks this morning. I work for a company called Adaptimi, based out of Ireland, and we have quite a specific use of AI in our organization. We specialize in adaptive learning, which seeks to personalize and optimize the delivery of learning content to foster better learning outcomes, increase engagement, and have goal-directed progress for our learners. It is an absolute honor to be with you today, and we have a really diverse and interesting set of speakers covering a wide range of topics related to AI. So I hope you'll enjoy our session today, and thank you again for coming. For our first session, you may have all have heard of generative AI, but the topic of our first talk is degenerative AI. If the generative AI revolution has already hit its limit, what is the next step in its evolution? I'm delighted to welcome to stage Dr. Sabri Boughorbel. Dr. Boughorbel is a scientist with the Qatar Computing Research Institute, or as you know it better, the QCRI. Doctor, please.
Thank you. Thank you. So today I'm going to talk from my perspective of a researcher looking at challenging GenAI in general. And we've seen a lot of success stories in these 2 days. And I want to look at the kind of roadblocker for AI. What's going to be the challenges that researchers need to tackle in the coming couple of years? So I'm going to have 3 parts of the talk. First, I want to review the AI progress so far, and then I'll talk about a couple of challenges that I consider highly relevant to be addressed. And the last part would be looking for sort of solution and directions to tackle those challenges. So first, let's quickly review under the hood how we build the GenAI systems. So we'll focus in this example only on like text-based models. So we'll start with a lot of text data. So we have 2 phases of pre-training and post-training, and those 2 phases, they have different requirements in terms of data, in terms of compute. And in pre-training, the objective is to mimic this large data, basically trying to predict the next token, next word. And by doing so, the models learn and is being exposed to a lot of diverse types of data. And then it has the ability to play different roles and being able to also take different personas. So in post-training, the objective is slightly different. So the goal is to maximize the preference of humans. So we want these models to generate responses that are likely to be endorsed by humans. And in terms of compute requirement in this phase, it's a lot less heavy than in pre-training. It's probably in the order of a few percent compared with the pre-training phase. And ultimately, we end up with a chatbot that we can interact with, that we can query and ask questions and give tasks. So let me review briefly the AI progress, and one of the key indicators of this progress was the compute put into building these models. And in this graph, you can see the evolution or the progression of training compute for different models in the last 10 years. And you could see that the rate of progression was around 4x, 4 times increase per year in terms of computer requirement to train these models. And such progression have never been seen before in any of the technological evolutions in the last 10, 20 years, comparing mobile adoptions or even human genome sequencing, and even Moore's law that is only like 1.3 times increase per year. And there is a reason why specifically AI progression is going through the compute direction, because AI performance is highly predictable. And this is coming a sort of physics of AI. There is rules that governs the performance improvement in AI. This is called the scaling laws. And in the graph here, we see like the sort of error that AI makes if we train it longer, if we give it more data, or if we put more compute in it. So this like physics of AI tells us that the more compute we throw on the data, the larger the models, the better performance we can achieve. And so this is seen in pre-training, but is also translated into downstream tasks performance typically. So the bet of the field is that probably we can reach through the scaling approach a moment where capability of this GenAI system would really explode. So for example, from GPT-2 to GPT-4, there is an increase of 1,000 times in terms of compute to train GPT-4 compared with GPT-2. And the progression we are seeing now probably will achieve the same order of magnitude in a couple of years between GPT-4 and the next generations. But the whole question of the field, will we be able to, given this amount of compute, will we be able to have these sort of explosions? And if this happens, then all kind of economic growth, automations could be possible, and that's why these huge investments are happening. So another side of the AI progression is looking at monetizing AI. And I guess the first player that is taking advantage is the hardware vendors, NVIDIA. So NVIDIA is projecting approximately 100 billion revenues from data centers and GPUs. So other players like OpenAI have seen revenues flowing at the rate of doubling the rate of revenues every 6 months, and Microsoft as well. So that's promising. So the field is responding to this investment, but the whole question is whether this is sustainable. The approach of scaling these models in terms of data and compute would reach the point of return on investment. So recently we've seen in the news some sort of worrying signal that this approach is like reaching a ceiling. So some of the thought leaders have mentioned that GPT-5 training is a sort of plateauing, and also looking at different benchmarks like MMLU benchmark and other ones. We see really incremental improvement in the last year or so. From GPT-4 breakthrough, only very limited progression we can see overall. So now, probably answering this question of whether we reach a ceiling, we want to address two challenges that this approach of scaling can face. The first one is this data wall, meaning that probably we're going to reach a sort of limit in an ability to add new data. And the second one is about the scalability of this approach in terms of infrastructure. So this graph shows the evolution and the progression in terms of data consumptions of models training from GPT-3 using only in the order of 100 billion words up to Llama 3 and Qwen using in the order of 10 trillion tokens. This progression is hitting a limits of human data generated in the green curve, which is estimated about to be around the 300 to 500 trillion tokens human generated data. And the statistical models estimate that around 2028 to 2023 will exhaust all the available human generated data. And then we will not be able to scale in the same way currently we are doing by just adding more data. Of course, these approaches also include sort of overtraining, so training on multiple times the same data, but still, that's going to hit like a limit very soon. So looking at the availability of data, there might be other places where we can tap on data, not only on indexed web, but looking at, for example, at enterprise data, where it is locked behind walls. So as well as looking at other modalities, like looking at video, images, audio, that potentially could allow this scalability to go a little further. And another direction which we see trending in solving the data limit issue is generating synthetic data using GenAI. And currently, I've seen some statistics that around 50% of the data being generated currently is synthetically generated by other AIs. So that leads to an example that has been recently studied, which is called Degenerative AI. It's relatively a sort of controlled example in an academic setting where you take a bunch of human-generated data, you train a first model with it, you synthesize a lot of data, but you train a next generation of models based only on synthetic data. And you keep doing this for multiple rounds of training only with synthetic data, iteration by iterations. And so the last model actually starts losing capability. It starts losing sense, and kind of this word model it acquired in the beginning, slowly it gets lost. So the same kind of experiment has been done for images. So this example is more visually, we can describe better. So this is the first round of images generated by a model and being used to train the first round of models. And if we look at the outcome, then you see that the models start losing capabilities and start slowly degenerating until you lose completely the quality of the input images. And this is just a sort of toy example of problems that could appear using heavily synthetic data. Especially currently, we are not able even to differentiate between human data versus AI-generated data. So that's one challenge that the field is facing in the future. So the other one is about scaling the compute. And Silicon Valley is racing to the 1 trillion data center, and that's gonna go from currently we've seen models trained on a data center with 100,000 GPUs costing $1 billion, and I think in the 2 years we will see models scaling at 1 million GPUs using 1 gigawatt of data centers. That's going to be massive. This is like the 1 trillion cluster estimation is that we want to use 20% of US electricity. This is insane. So first thing that the scaling of training going to hit is energy. So something to explore. There have been actually discussions whether, for example, Middle East, which is very rich in energy, could host these data centers, but that's beyond the core of this presentation. But one limiting factor for scaling going to be the first thing is energy. Other limiting factor, as we discussed, would be data, but chip manufacturing also is of concern, as well as other hardware, latency between all this infrastructure. So I've covered now these two issues and challenges that AI field are going to probably face, which is data and the scaling of the compute. So let me now revisit the machinery that we build GenAI with it to kind of tackle this issue. So we've seen this pre-training and post-training requiring a large amount of compute and data. Now the trend is to shift the problem into the inference time. So while asking the questions, these models are going to spend a lot of time with a lot of tricks to solve the question. So instead of putting a lot of emphasis on the pre-training, post-training, we're going to do a lot into the inference time during a real usage. And that's going to come through splitting these tasks to a lot of agentic agents, a lot of distributed models that are going to take the tasks and split them and solve it. So just to give an idea how this could gain in terms of compute. So imagine we trained a model with a budget of, an amount of budget of compute. We have two ways to improve the performance. So imagine we have a performance of 0.5 on a certain benchmark. So one way is to just scale the way we used to, using pre-training, large compute, large data. The other way is to use these post-enhancement techniques, and which probably will take like less than a fraction of the compute required for the other track. And then the two approaches would reach, for example, a performance of 0.7 on a certain benchmark. And the compute equivalent gain gonna be how much compute we saved by these techniques at inference time. So here, for example, it's gonna be a factor of 5. And charting the space of approaches, not gonna go in much in details, but just to give you an idea, there are techniques related to enabling tools for these GenAI techniques, allowing the models to use API, to query the web, to use calculators. These, open up a lot of capabilities, during the usage utilization itself. And these two charts, the one on the left shows the gain and reduction in compute that is invested in one single time. So, for example, we need to fine-tune these models for using, for example, using tools. But once it's done, then at inference time, compute is not needed at all. So the model is now able to infer and know when to use a calculator, for example. And the second graph is showing the compute required during inference. So, for example, if we use few-shot learning, that's going to increase the cost of context, and also that also propagate to the compute. But still, both cost in one-time cost, also inference cost, will be way smaller than the scaling approach. So also we've seen recently an example from O1 from OpenAI, where they pushed even the limit of these approaches by updating the weight of the model for each query the user come up with. Of course, this update is very smart and very cost limited, but they show that by updating the weights of the model at inference time, they are able to improve even better than doing the pre-training updates. So I expect that we'll see a lot of these approaches in the future, where we are shifting the paradigm from the large scaling approaches towards more kind of unleashing AI capability, unleashing at inference time. So in conclusion, we've seen how AI progressions depended or still depending on scaling the data as well as the compute. But this approach probably is reaching a limit soon. That's a sign in the whole field that these approaches, due to limited data, due to the constraint of scaling the compute, we need to shift to new techniques. For example, the ones I mentioned about doing inference time trainings, and that seems to bring a lot of gains in terms of performance and keep the field moving forward. So, of course, these new techniques are mainly focusing on specific domains like reasoning domains or niche domains. So the question whether this progression, like this general progression, will continue as we expect or not, that's we need to see and observe, and hopefully, I think there is an exciting time to see how this shift from old to this new ways of improving and keep the field very active. So that's all. Thank you.
Dr. Boughorbel, absolutely fascinating presentation. I don't know about you, but maybe a lot of us are guilty of having the expectation that improvements in the quality of generative AI are not only going to be never-ending, but they will continue to be exponential. Some of us might have been familiar with the challenges around infrastructure and data processing to achieve those improvements, but a really fascinating talk to learn more about the limitations of the data and this phenomenon of recycling generated data and the degenerative effects it can have on output. So absolutely fascinating, Dr. Boughorbel. We have time for just one or two questions, so if you want to raise your hand. Excellent. And I'll just repeat the question so the rest of the audience can hear.
What's the benefit of training on sorry.
Oh, sorry. Thank you.
Thank you. Very interesting talk. My question was around synthetic data. So you mentioned that real-world data is really the commodity here in terms of us reaching the limits of it very soon. And you also talked about how synthetic data leads to the degeneration of the model. So is there any benefit to actually training on synthetic data, and should that be avoided in cases where you're trying to train your models?
Yeah, so I mentioned actually the example I mentioned is more sort of academic setup where the models are trained on 100% of synthetic data. So currently the approach is to kind of balance, make sure that the synthetic data is under control, like probably below 10% of the whole model data, as well as also covering only gaps in your data. And so far it has been shown that it even boosts so far the performance. But I kind of take an extreme example where we don't even know what distinguish between human-generated data versus real data. So it's more sort of alarming example rather than reality like now, actually.
Yeah. And I know for me, certainly the visualization that you provided there of our generated farmer slowly getting worse and worse over time as it's continuously trained on generated data, really visually compelling and impactful illustration of precisely the problems. One can imagine the quality impact to generated text, generated video, other phenomena. So really beautifully visualized. We have time maybe just for one more quick question. The gentleman, I'll come to you. We'll come to you next.
Okay, thank you. So you mentioned in your lecture that you suggest to move maybe that data processing to be on the countries which have low energy cost, which is really a brilliant idea. But do you believe that this will move the bottleneck to become on the data transmission part? Like if the processing problem is solved, I think then the next problem will be maybe the data transmission. So what do you think from the academic point of view?
So one of the graphs I showed where we have all the kind of limiting factors that play roles. So energy was the first. Second one was, I think, data constraint. Actually, latency between nodes and probably even data centers seems to be the least of concern, actually. The network connectivity can reach up to petabytes of data per second, actually. So in that sense, that's not the most worrying part of the scalability issue.
So, ladies and gentlemen, we will have to say goodbye to the doctor now. If you want to speak with him, you may make yourself available. I know there were lots of people who wanted to speak. So, once again, please put your hands together.
Thank you.
Thank you. That was great. Excellent. Thank you so much.